Welcome to Molecules and Ions. Alright, so we need to define what exactly we mean when we use certain terms. So an atom is a single particle of a certain element, and this is the smallest particle that will act like that element. If we get any smaller, so we know that atoms are composed of subatomic particles, protons, neutrons, and electrons. The protons and neutrons are composed of quarks. But if we get any smaller than an atom, then that particle doesn't act like that element anymore. Now it acts like a proton or a neutron or an electron or a quark. And then we have molecules. This is a single particle of a certain compound. Compound is different than element. And the smallest particle, a molecule is the smallest particle that will act like that compound. If we get any smaller, we get to atoms. Each molecule is made up of multiple atoms. So our molecules are composed of two or more atoms that are covalently bonded together. Note here that I've specified covalently bonded together, not ionically bonded together. So this is something like water. So in water we have, in one water molecule, we have two hydrogen atoms and one oxygen atom. Those are covalently bonded together. In carbon dioxide, we have one carbon atom and two oxygen atoms bonded together. Now, a chemical bond is a force that holds two atoms together, two atoms together. So we can't get more than two atoms bonded together because not with one chemical bond. We have to have multiple chemical bonds. A chemical bond holds only two atoms together. Right? A molecule can have more than two atoms in it, but then it must contain more than one bond, more than one chemical bond. So water has two chemical bonds, one that's drawn here and one that's drawn there. Now these are just representations of the chemical bond, right? We don't have little sticks connecting together our hydrogens and oxygens, and we don't have little sticks here. So here we have a double bond connecting this oxygen to the carbon and another double bond connecting this other oxygen to the carbon. Here we have single bonds. So we have different ways of representing molecules. We have chemical formulas, structural formulas, ball and stick models, space-filling models. So the chemical formula is a collection of element symbols and subscripts showing how many atoms of each element are present in the molecule. So for something like hydrogen, we have our element symbol H, and we have a subscript 2. That subscript is telling us how many atoms of the element immediately to the left that we have. Well, the element immediately to the left is hydrogen, so we have two hydrogen atoms in a hydrogen molecule. In a water molecule, we have two hydrogen atoms, because it's H2O, and we have one oxygen atom. Now note that if we have one, we don't have to write the subscript. We ignore the subscript, we just leave it off. And so if there's ever not a subscript written, it really means one. Just like in math, if you have X, it really means 1 times X. So ammonia, we have NH3. There's no subscript on the N. That means we have one N, one nitrogen. We have 3 hydrogens in ammonia. In benzene, we have C6H6, so we have 6 carbon atoms and 6 hydrogen atoms bonded together. Now, note that this only tells us which atoms are there and how many of each atom we have, or each element we have. But it doesn't tell us how they're connected together. And that's where we get to a structural formula. So a structural formula is a drawing showing the chemical bonds within the molecule, or at the very least, how which other atoms each atom is connected to. So they may or may not actually show the shape or the true shape of the molecule, right? It shows us how they're connected, but not necessarily the correct geometry between them. So we could write hydrogen this way with an H and an H and a line in between them. That line representing the chemical bond in between. We could write water this way. Now note that this is actually showing something of the true shape of the molecule, but we don't have to write it that way. We could represent water like this, but note that this is not bent, whereas that one is. Water actually is a bent molecule, but this is a perfectly okay structural formula. Note that this structural formula is vastly different from a different structural formula that's, let's say, like this. This would be a different molecule than that one, because here we have a hydrogen atom in the center, and there we have an oxygen atom in the center. Right? This one doesn't actually exist anywhere, but this one does. Right? This one is water, and that one is not water. Water doesn't look like that. So again, here we have our same four molecules: hydrogen, water. We have ammonia here. But now we can see that our nitrogen atom is in the center, bonded, singly bonded to each of the three hydrogens. But again, this is not geometrically the right shape, but this is the way that our atoms are bonded together. Here we have benzene showing the carbon atoms all bound together in a ring, and the hydrogen atoms each bonded to one of our 6 carbon atoms. You can see that our carbon atoms each have one single bond to a hydrogen, one single bond and one double bond to one of the carbon atoms. And so we can see how they're connected together. In this case, the shape is actually correct. In this case, with the ammonia, the shape is not correct. All right, a third way is with a ball and stick model. This is a three-dimensional representation where each atom is represented by a ball and each bond is represented by a stick, holding two of the balls together. In this case, the ball and stick model is, or should be at least, it should be geometrically correct. So when we have our water, it needs to be bent like this. Our hydrogen molecule, well, it's just 2 atoms connected together. Usually we color code our ball and stick models. So usually hydrogen is white, so hydrogen is white in each of these. Oxygen is usually red, nitrogen is usually blue, and carbon is usually black. And so you can see here, now we can see that this structure for ammonia is not exactly the same as on the last slide. On the last slide it was sort of T-shaped. In this case, it's a three-dimensional shape. It's no longer a flat T. Now we have a sort of a triangular pyramid kind of shape here. Again, there we still have our 6-membered ring. And the last type we have is a space-filling model. So here, we're in the last model with the ball and stick model, we're basically showing where the nuclei are, and we're drawing sticks between them. Here, we're showing, we're trying to represent where the electron cloud of each atom is, and showing that on the last slide, it appears like our hydrogen atoms are separated by a good distance, and there's some empty space in between. But you can really see that our molecule really looks more like this. It's not even 2 circles connected together. They're really overlapping a good bit. And even here with the water and the ammonia, they're overlapping quite a bit. So the electron clouds of the hydrogen and the oxygen in this case, or the hydrogen and the nitrogen in this case, they're really overlapping a good bit. They're really penetrating into each other quite a lot. And you can see the benzene really looks much more like a disc instead of a ring with an open center to it in this case. All right, so now we turn to ions. So we had been talking about atoms and molecules. Atoms and molecules have a neutral charge to them. Ions, an ion is an atom or a collection of atoms that has gained or lost electrons, and thus it has a non-zero charge. It has some charge associated with it that isn't zero. It's not neutral. It's got a positive charge or a negative charge, and we give positive charges and negative charges, positively charged ions and negatively charged ions. We give those 2 different names. We have anion and cation. So an anion is a negatively charged ion. This is formed by gaining electron. Remember, an electron is negatively charged. So if we gain electrons, we're gaining negative charges. So we'll get an ion that has a negative charge. We'll get an anion. A cation is a positively charged ion. This is formed by losing electrons. Again, remember, an electron is negatively charged. So if we take an electron out, we're removing a negative charge. We still have the protons in the nucleus. So as we remove a negative charge that is balancing out those protons, our atom becomes an ion that is positively charged, or more positively charged, at least, less negatively charged. So the way I remember which of these is positively charged and which of them is negatively charged, I have a cat that I like. So to me, cats are positive, so cations are positively charged ions. Anions are negatively charged ions. So, ions are repelled by like charged, by same charged ions, and attracted by oppositely charged ions. So, an anion repels another anion, but it attracts a cation. A cation repels another anion. A cation repels another cation, but attracts an anion. This attraction between ions is called an ionic bond. So this is different from a covalent bond. In covalent bonding, the electrons are shared. In ionic bonding, you actually have separate ions. You don't have neutrally charged atoms like you do in the covalent bond. So ions don't form molecules, but they do form crystals that contain many ions of each charge. Now, they don't form molecules because there isn't something specifically connecting one ion to another ion. Yes, there's an attractive force there, but there's nothing special about this cation as opposed to a cation from over here, let's say. And so we talk about ionic compounds in terms of formula units. Formula unit meaning this is the simplest number of ions and cations that combine together to give us a neutral overall charge. So something like sodium chloride, we need one sodium ion and one chloride ion to combine together to give us sodium chloride. So the formula unit for sodium chloride is NaCl, one of each sodium and chlorine ion. But they don't form molecules. It's not technically correct to be talking about a sodium chloride molecule because they're not forming molecules. The sodium and chlorine ions aren't specifically associated with each other in the way that the hydrogen and oxygen atoms are in a water molecule. In a water molecule, when you dissolve water in something else, those hydrogen and oxygen atoms, they stick together and they move throughout the solution all together as one group. But if you dissolve sodium chloride in something like water, those sodium ions and chloride ions, they split apart and they're able to move around independently of one another, so they're not bound to each other. So, again, we need this concept of formula unit to differentiate from the molecule of a covalently bonded compound. But again, it's still the smallest unit of an ionic compound that contains a balance of positive and negative ions to it. So we have something like sodium chloride or magnesium chloride as MgCl2, iron 3 chloride is Fe2O3. But again, in each of these cases, those 2 iron and 3 oxygen atoms, ions, 2 iron ions and 3 oxide ions, they don't have to move around all together. You just have to have the stoichiometric ratio of 2 iron ions and 3 oxygen oxide ions near each other, but they don't have to be in a specific orientation like, say, water has to be connected together. So I mentioned that ions could be more than one atom. We can have polyatomic ions, so poly meaning many, atomic meaning atoms. So polyatomic means many atoms contained within the ion. So polyatomic ion contains 2 or more atoms that are covalently bonded together, and the whole grouping contains a charge. So this is essentially a molecule, a covalently bonded molecule that has gained a charge in some way, either by gaining or losing electrons. So this is something like ammonium, NH4+, nitrate, NO3-, hydroxide, OH-, or sulfate, SO4, 2-. Now we have a number of different common polyatomic ions that will come up, and I'll explain more about what they are when we get to naming. But that was molecules and ions.